So this is going to be a demonstration of synchronizing a pair of AC three-phase generators on a common power grid. What you see here are two generating stations that we have built for a protective relays course here at Bellingham Technical College. Each generator is a three-phase unit. It's actually a Delco ringing alternator for a heavy-duty truck. We're spinning it with a three-phase motor connected to a variable frequency drive so you can change the speed very easily. This is simulating a generator at a power plant being spun by a steam turbine or a water turbine or something of that nature. What we're going to be doing here is using these to demonstrate power grid operations, and in this case today, synchronizing. So what we have here, just to show you, we've got the generator, the motor, our speed control, step-up transformers, some current transformers to measure the current, and then we have our circuit breakers. We're using a pair of three-phase contactors as circuit breakers. I'm going to close one of them here, and we've got it set up to be self-latching. Right now, this generator's output is now powering this grid, those three wires you see right there, three-phase power, with about 140 volts or so. That circuit breaker is currently open, and we have three neon light bulbs connected across the poles of each circuit breaker contact. And you'll see these light bulbs are blinking. What that's telling us is that these two generators are not in phase with each other. They're both putting out three-phase power, about the same voltage, but one's going a little bit slower than the other one is. And because one's going slower than the other, they're continually falling in and out of sync with each other. You can think of this simplistically as being like two batteries being connected in parallel. If we wish to connect two batteries in parallel, they must be of the same voltage and the same polarity. If we get one battery backwards, bad news. Hook them up together, you get a short circuit. So you want to hook up batteries together in parallel with like polarities. Well, AC generators are kind of like batteries that are spinning around. So as they spin around and come in phase with each other, they have the same polarity. But if you let one of them spin at a different speed until it's opposite, they've got opposite polarities. If you try to close that breaker then, bad news, short circuit. So what I'm going to do is change the speed of this one generator over here, and you'll see the blinking rate change. So right now I'm going too slow. If I go slower yet, you see the lights blink faster. If I go slower yet, it blinks even faster. The slower this generator goes in comparison with the other one, the faster they roll in and out of phase with each other. So in order to make these suitable for synchronizing together, for closing that breaker and getting them in parallel, I need to get them in phase to the point where these lights are off and are staying off. So watch me as I speed this generator up. I'll speed up the generator, it's blinking slower, speed up the generator, blinking slower. So what we see here is a case where the sine waves in these two generators are very nearly the same frequency, and they're rolling in and out of phase with each other a little more than once a second or so. So imagine 60 hertz versus 59 hertz. That's about what we're looking at here. I'm going to increase the speed just a little bit more on the slower generator until I get a slower blinking rate. Then I'm going to wait for the lights to go completely dark before I close my breaker. I don't want to close them when I have light, because that would be closing a breaker across a substantial voltage difference, and that would be a transient event, a current that would shock the generators. I'm going to speed this generator up a little bit. And now they're parallel with each other. What's happening now, when the generators are parallel, when they're on the same grid, is they are now electrically coupled with each other. And if one tries to spin faster or slower than the other tries to pull it either up or down to speed, and they tend to stay in sync. It's almost as though we have a mechanical coupling, kind of a loose mechanical coupling between the generators being on the same grid. The tightness of that coupling, or the rigidity of that coupling, depends on our current capacity on the grid. How many amps we can source or sync from each unit. Basically tells us how much torque each unit can correct the other with. So right now, when we have them in sync, and we have these two induction motors powering them, the ability of the induction motors here to slip is what allows these two generators to actually stay in phase with each other, even though the motors would actually be having them spin slightly different speeds if left to their own devices. I can unsynchronize the generators here, and you can see I go back into a condition where they're rolling in and out of phase with each other. I can go synchronize again, right there, and now they're synced with each other, and they're going to stay locked in sync unless I were to shut one down completely, because one generator in this case does not have enough current capacity to keep the other one going as a motor. So that's a demonstration of synchronizing two generators. and using sync lights to do so.